second. That was the wrong screen capture from using AMD Ryzen the other day. Welcome everyone to this live stream. Starts already well with streaming the wrong screen. Anyway, reduced instruction set computers, architectures. We do so much work on this vintage Unix stuff. Well, vintage and vintage. Some of the stuff is still these days, like RISC-V. In a previous live stream, I showed you the instruction set format here of RISC-V, which I found for the most part pretty nice sorted here. If you are interested in just RISC-V and the latest and greatest modern stuff, just rewind some couple of 50 or so videos. And I thought I give you a quick summary how this differs, because we recurrently work here on SPARC and MIPS and stuff, and PowerPC with Octane and P3 and so on. And I wanted to give a quick overview. RISC, of course, stands for Reduced Instruction Set Computer or Architecture. And this reduced does not mean that they are less powerful or less complex. Certainly they are not only powerful, as well the P3 or SGA Octane certainly has shown, but also they are certainly complex with multi-core and single instruction multiple data, all this stuff. Still millions, if not nowadays billions of logic gates there, transistors and stuff, but this mostly mean less complex in the form of each and all the individual instructions. And I wanted to take a quick look here today, so the stream should not be the most long unless you ask very many questions. Many of those RISC designs, of course, include ARC. Many of those you have maybe not even heard, like ARC, but also Alpha of good old DEC Alpha fame, AM29K, which was an AMD. Also probably very few of you ever heard. I think even some SCSI controllers or maybe even some graphic cards use those. ARM, AVR32 Blackfin, which by the way we also have here DSP. Intel 8060, 960, which also were used on graphic cards. The Motorola 88000, which was not the most successful successor of the Motorola 68K. MIPS PA RISC, which we also had here on this channel. PowerPC, RISC-V, latest and greatest Super H, also from console fame there, and SPARC, among other things. So if we take a look on RISC-V, what they all have in common, and this is what I wanted to share also, they are actually not very far apart. You would think they are entirely different, but actually they are pretty similar. So this, of course, here being RISC-V from latest and greatest open source, open hardware fame, and details in this previous video, but you see here there is opcode, so this is extremely irregular. That is what a property that all of those reduced instruction set architectures share. So we have here a really regular layout of opcodes, and what they here in RISC-V name R, I, S and U type, depending on what kind of immediate or other arithmetic and so on functions this opcodes perform. And when we take a look on those much older generation instruction set architectures, this here is I think MIPS. So much to scrolling already down to the so this is MIPS Architecture for Programmers Volume 2A, MIPS 32 instruction set architecture. And it's not so difficult. Also, by the way, back in the day, I even forgot about this. So of course, back in the day, you would have had some nice hardcover print books just showing exactly the same thing. I just don't have neither Intel, so this is just some 68 HC12 what we have here in the office library. Unfortunately, I neither have x86 nor PowerPC nor MIPS in such nice printed book form, but maybe I try to find some the other day. But certainly nowadays is PDF stuff much more convenient. Scrolling, I have so much to scrolling already. So when we take a look here, how does this differ from RISC-V? You see, so this is of course an example instruction just to show how this text here is written. special something, RD, so registers. Just a stupid example, just let's scroll to some more useful ones. So of course, all of those stuff is pretty similar, just as I said, so add for adding stuff, register source, something. Let's just try to find here. Already found a better suited field here, just that I scrolled up to find what we are looking for. Come on. So instruction set, yes, that's what we wanted to see. Let's take a look to some absolute here value floating point. Absolute value, not the best example, but you see here, actually this is really not the best example. Anyway, here is add, so this is a better example. I've so much to, probably I had scrolled to a better example, but whatever. So you see an instruction format just similar to RISC-V here. Opcode, register, destination, special function. This is just basically extending this opcode range, but for details of previous video. Otherwise you have 6-bit or 7-bit for the opcode. And so for example, for this immediate value, but otherwise if you have more complex, reduced instruction set architecture, but that already gets more complex, meaning all these variations of add, subtract and floating point and whatnot. And so registers. And you see here for the opcode for immediate meaning, you have some magic value like bit ending ORing this to some hardware register. So you might need some magic constant like 0, 1, 1, 0, whatever you want to check in some SCSI controller or VGA graphic array. And you might need to load some immediate values to write to the hardware, comparing the hardware. And this is why loading something you certainly do not need any of those source registers, because certainly only have some immediate constant, and this is why this only has some destination register. And this MIPS stuff, just the same here, extremely similar. Adding here apparently according to this documentation 000001. Maybe this also, I'm not sure. Don't remember them, all of them. But then you see also register destination, and then they name here, unfortunately, the sources. They don't name this source 1 and source 2, but register source and register T for whatever historic naming convention there. And special value again also for encoding more details. And yeah, welcome everyone in the audience if you have any questions to this. And when we take a look to on PowerPC, I found here a really nice article in the IEEE Spectrum or whatever that was. Oh, wait a second, this is not IEEE Spectrum. That is IEEE Explore, some original article from Ed Schiller, so from IBM, and Keith Diefendorf from Motorola, promoting this here when this came out. So this is an original article from 1994 when all this hot RISC stuff was hot and new. And here you see in just this article that they illustrate and lay out this here just as that. And also what all of those architectures basically have the same as 32 general purpose registers, in contrast to x86, which just has a mere like 6 or something plus some special segment and source and so on. Maybe we take a quick look at the end. But so all this RISC is extremely similar, mostly 32. Why 32? Because that is what some people started with, and then certainly you see here with this bits, it makes sense if you have a regular, nicely divided in instructions and dividing the bits in the instruction. This is usually what people end up with. Otherwise you could use 16, certainly a multiple of power of 2. But if you, otherwise you have only 16, so this making best use of the silicon, most people in the end of the 80s and beginning of the 90s, most people like MIPS, PowerPC and SPARC, they decided we rather have really many registers, making up for some loss, potential loss of performance, because these instructions are all 32-bit wide. That is a huge contrast to x86, where you have a variable length instruction of 1 byte up to 32 or 37 bytes or whatever the maximum theoretical length might be. So because you lose some performance of less densely compact instructions in memory, and also you need more instructions actually, because in x86 or other complex instruction set architectures you usually have load, like you have memory references. So in x86, which probably maybe we should have opened for illustration purposes, you have many of those, would this be instruction, okay, let's load here some Intel stuff. So in complex instruction, unauthorized, seriously. Breaking the x86 architecture, what was this from? Oh, black, no, we don't want to break it though. Probably this was mentioned in another, let's see if, anyway, all of those, let's click here on something like add, which by the way would have been. So in CISC you can directly load memory, load and store memory in many of these instructions. Actually did not want to mention this. So there you see in the example here of x86, the shortest instruction is just 1 byte. Ironically, 00 is add, so that is of course a numeric encoding of machine language there in memory. So 00 register is add register, register or memory, and this is what one drawback of reduced instruction set is, that not only do you already use more memory for regularly all instructions being the same width, usually 32-bit, but additionally you need many more of them. So on CISC you can load and store immediately in all those arithmetic and whatnot instructions. On RISC you need load, compute, store, and this repeated many times. Of course, why did they do this? They did this to reduce the complexity in the CPU and reach much higher frequencies and better out of order and multi-scalar execute them. Comments in the audience. Joe writes, x86 is what never learned himself, too complicated. They only teach MIPS in college and happy, except it's not used widely. Yeah, so I actually grew up with x86. Maybe we discuss some more details at the beginning. So from the efficiency standpoint, RISC, as you see, with totally completely strictly aligned instructions of usually 32-bit, it is not the most efficiency, and why x86 actually always was not too bad in terms of efficiency in the memory layout. But and then additionally requiring more instructions for explicit load and stores of all the values. So PowerPC here, which I wanted to show you on this. So in this old book of exactly this kind of print here in this article, the same 32-bit 32 general purpose registers on PowerPC, the same concept, RISC of course, load, store, and all the instructions. The only thing is that PowerPC, as far as I've experienced, is one of the more complex of the reduced instruction set architectures, because this instruction encoding is much more complex, as also seen here in the modern specification here. When we take a look at RISC-V has here this base instruction format, R, I, S, and U type, which plus a couple of, theoretically a couple of more with a little bit more fine-grained. But PowerPC also has quite some variations of those, which probably, So if you take a look, because for all the different compare and load and sign extend, and this is why you think you need just like 20 instructions, but when you really build an actual microprocessor, you need many more of those instructions, because you need add with compare. For example, I think PowerPC has all the instructions, many variations of add, and because what do you need this compare for? You need this compare for to make decisions based on adding up, multiplying some value, and like for example bound checking, you compute some location in memory and then you want to bound check this, and this is why for example PowerPC I think has many of those instructions in two variants, either also setting conditional registers, whether it is overflow or less or equal 0 and similar stuff. And this is how even this reduced instruction set, simple forms of IBD and stuff quickly become more here, X form, XL form, XFS form, and so on, so much to MDS form. So yeah, that is not so reduced anymore. And SPARC, if you take a look on SPARC, again extremely similar. For example, here also I think the highest bit set, again, correct me if I'm wrong, leave the comments below what you think. This is only a quick summary between working on commercial products, doing a little bit of open source work, and figuring I should also better do some live stream today. And so if I say something wrong or if you have additional remarks, just leave comments below. For example, SPARC, to have a jump, so a calling another subroutine, this opcode format is only 1 bit. Probably it has either this bit set or not set. Probably we should check this, but here's call, so format, opcode. So I think 1 might be call. So this, if you disassemble or look on SPARC machine code and the first bit is set, again the same layout, fixed 32-bit instructions, and if the first bit is set, then that is a call. Why do they do this? Because they want as many bits as possible for the memory location for the jump, and that is why they have here then 30, wait a second, somehow, what is, not sure what is with bit 30, anyway, 30-bit displacement, meaning 30-bit jump location. Usually what many of these RISC architectures also do is, because the instructions can only be aligned to a multiple of the words, of 32-bit words, is that this jump displacements are anyway shifted by 1 or 2 bits, usually for only allowing to jump to memory locations aligned by 4 bytes. Certainly makes sense if the instructions anyway need to be aligned and anything in between wouldn't make sense. It makes sense to save some bit here. Yes, Joe writes circle, yeah, register circle. We are getting there in a moment. That is register window, a very unique thing to SPARC. So you see the general layout here pretty similar. Format 2, set high branches, something here. You see the opcode format here, a couple of more bits, but again for 22-bit immediate values, similar to MIPS and also RISC-V. So RISC-V was here for however, whatever bits this are, 12 to 31 should be 30 something of 12, 32 something in the area of 20-bit immediate. And oops, also I moved this out of this. And if you need more bits than this in RISC-V, then you need 2 instructions, right? So if you need to load 32-bit magic value, or in a 64-bit RISC-V variant, then you simply need to run 2 or 3 of these immediate load instructions and shift and order them together, which I'm sure there are dedicated instructions. MIPS, for example, has to load higher bit count. There is even, probably is this our MIPS, higher, let's see, do we find this immediately? Maybe not. How MIPS is doing this by having special instructions to directly load higher and middle. So they have like load lower, load high and load higher instructions to fill the registers with magic constants of loading more than 20 or so bits. So on the SPARC side, 22-bit immediate here is this here. This adds up 0 to 21. And if you need more, then you need to shift and and this together, and shift and OR this together. And I'm sure the dedicated instructions for that. And remaining instructions here, format 3 for destination source register, additional operands, just similar to spreading here also, to keeping this. Why do they do this? You might think, why is the opcode here in the middle? They do this for efficiency reasons in the silicon. This is exactly why RISC-V is also doing this here. You might wonder, why is the opcode here split into opcode and then function and function 7. By the way, they call this function 3 and function 7 because these are 3 and 7 bits from 12 to 14 and from 25 to 31. And they together form the final opcode value. And on SPARC, exactly the same. And they do this to keep the destination register here in the same location to simplify decode and execution in the RISC core there in the silicon. Because if they would move this opcode here, then they would move this destination register location. This is why this, for the hardware, it doesn't matter where the registers are, but it might matter a little bit in efficiency space to have the decode and execution just directly using those registers there. Otherwise, it doesn't matter at all if these opcode bits are spread over wherever in the instruction there. So you see, totally different, totally similar, totally the same, completely different, completely the same concept. And the only thing here different, what Joe already mentioned there, is this register window, which, where would that be? Somewhere, maybe this was before there. So SPARC is one of the few instruction set architectures that has a sliding register window. That means all the other RISC instruction set architectures, they have like 32 registers, and SPARC has like, I don't know, 128 or something of that sort. Do they even write this here? They write it to 8 global, or not illustrated, something. And so how this works is that internally they have more registers, and this, when you call a subroutine, this register window can rotate by, I don't know, 8 or so registers, n windows equals 8. And this theoretically meant not to save and restore registers, so that the called procedure can just use temporary registers, and when you return, the register window is rotated back by 8 or whatever registers. The only thing is, of course, the hardware registers are not infinite, so if you run out of registers, however the hardware implements, maybe 128 or whatever that was, or 64 could even be implementation defined, and the operating system needs to have support for this. So because this register window certainly overflows sooner or underflows sooner than later, the operating system has support to trap this underflow if it runs out of hardware registers. So the Linux kernel, for example, on SPARC needs to manage this. Additionally, these are all the portability things that the operating system needs to take care, so that it saves all those registers and loads or resets this and provides a new space, a new set of registers to continue execution and fine-tuning this kind of stuff. This is the difference that makes the performance characteristics on top of all the other core and application binary interface, meaning which registers are used, how many are callie saved, callie, how many temporary registers are available. These are all the stuff. On MIPS we see this. On MIPS we see the original 32 application binary interface, the new N64-bit application binary interface, and then the new 32-bit application binary interface that is making more use of more registers, different calling convention, and so on. So you see all those details are pretty similar. They mostly, except this register window, differ by how they encode the instruction here in those formats. So what might be the opcode 1 in SPARC for a jump might be AND or whatever the MIPS designer have chosen. And this is why they, although they look totally similar, yet they are entirely different in terms of what numbers they are using. Certainly, if one bit is already different, then it's already not binary compatible anymore. And of course, on top of this, they have chosen their totally different numbers. That is, although all this RISC looks so similar, they are unfortunately not. I also wonder what history would have been if all those vendors would get their act together and MIPS, PowerPC, SPARC, SGI, IBM, Sun, and all the companies in between, Hewlett-Packard also with precision architecture, if they would have got all their act together and worked on one high performance RISC architecture, not only making this look similar, but also using all the same instruction and instruction format and competing, not only having compatible applications and theoretically maybe operating systems, but having a really strong competitor to x86, if this would have been more successful instead of this very much convoluted space of competing RISC architectures. One difference is also that PowerPC has a different use of flags. So many architectures have only one set of flags for comparing, like less, equal, overflow, and so on. Also, why does it not search for? I wanted to search for ZR. Also, of course, if the processors have floating points, then usually they have additional 32 or so floating point registers. Control somewhere here was floating point status and control register, and where would that be? Control register, I thought it was here. Somewhere here was mentioned, so PowerPC is one, again, different architecture exception in having more than one condition register. And this condition register holds the ALU, arithmetic logic unit, status information for testing by conditional branch instructions. So this CR is actually a collection of 8 independent 4-bit registers, CR0 to ZR7. Do they write 8? Anyway, whatever. Grouped together as one 32-bit register for convenience in saving and restoring the process state of, meaning with this they mean in functions and by the operating system. And those 8 control registers provide sufficient namespace so the compiler can schedule control register usage as it does general register to avoid data hazards, meaning instructions waiting for this data to become available in like additions and subtraction for comparing values. And this is very special. Not only x86 has only one set of flags, and many RISC architectures also do not have this. So this is very special. Actually, maybe I check another day. I'm not even sure how much use GCC is making out of this. This is also the difference between good compilers generating good code, like highly efficient, high performance code, for example, making the best use of this control registers, and this architectural differences between MIPS, PowerPC, SPARC, and certainly x86. The code generation in GCC, of course, quite similar for all the RISC architectures, except all those register windows, additional control registers, and certainly on x86 having this integrated load and store in all those instructions for memory references that otherwise you don't have on RISC. That is so far the basic overview, and if you take a closer look on x86, you see, if you think for yourself, if you would want to implement this for either you want to make a hardware startup because you think you can do it better than Intel and AMD, or you want to do this on an FPGA, what we also want to do soon with the RISC-V, Pico RISC-V stuff here, and you see, if you take a look on this nicely regular RISC reduced instruction set architectures or CISC, you will certainly quickly realize that it's a total pain to implement this variable length instruction decoding. So certainly it is much easier to do this in hardware, the RISC way of 32 bits, regular sized instruction and decoding those, than on x86 where you need to constantly look up, like it starts with this opcode and then what is this, and then it can also be on x86, you see just here it can be directly immediate, but for example here this is just adding, there you see how complex this x86 is. An example, totally unsystematic, you could say. This 8-bit opcode 04 hex is, you see, you can't even specify the register, so this is hard-coded to AL, the low part of the AX register, and this is just 04 in memory and then an immediate byte, and this immediate byte is loaded into AL, and this is, yeah, totally, yeah, as whatever randomly they made up there at Intel, and certainly not fun to write a compiler for, not fun to write silicon for, but that's what we are all using mostly today. And if you scroll over this, you clicked on this, you certainly see also this compare exchange is then 0F for some escape in some larger opcode range, and then B0 and B1, and then register or memory 8, 16 or 32 bytes. This is how x86 works, completely complex and extreme contrast to reduced instruction set architectures. Let's see what we have there in the comments. And no stack, I think SPARC register circle and no stack. Excuse me, too much talking today. RISC full opcode. Is the RISC full opcode address space used, or are there some opcodes reserved? There usually are some reserved for later expansion. Certainly they're also on MIPS and PowerPC. They constantly develop them. For example, on PowerPC you have also AVX, the Altivec vector instruction set. And so usually they left some opcodes unused for later expansion. And also RISC-V, as seen in my previous video, where we go through the whole RISC-V, or not the whole, but mostly. And here you even see that they plan for some extensions. So the MA, I think M was multiply, A was atomic, F is floating point, D was whatever, and so on. F was vector, and whatever all the other were. B was bit extension. And so they already planned for having some of those range free, and certainly all of them did, because certainly you always at MIPS Technologies or SGI back in the day, IBM, Motorola, they always knew that they certainly always had so much in their mind what they could implement next, but there's always so much time to market. So you probably naturally always leave some of this reserved for future expansion, for the next commercial product, for the next high performance upgrade. And so naturally they always left something for the next development step. And yeah, that's probably it for that. Joe thinks for pre-x86 machines were more RISC like VEX. Not all, there was also Motorola, and also this PDP-11 stuff. PDP-11 was using, so that was, how was this called? The design of the PDP-11 inspired the design of late 1970s, including the Intel x86, Motorola 68. I think this was CISC. Hello. No mention here. I think they were more like complex because they were usually special purpose PDP-11. So examples of CISC includes System 360, set architecture, PDP-11, VEX, and set 80, so Motorola 68K, Intel 8080, and Zilog Z80 family, and others, MOS 6502 and 8051 and similar. So basically CISC is how they mostly started, maybe mostly also because they built very tiny machines, so maybe usually they were really, of course it had a benefit. You see RISC has the drawback of wasting a lot of memory with its very regular instructions and requiring load and store. So that is maybe in the beginning when they used very few logic gates that they specifically handcrafted this for to making the first very small machines working at all. I could imagine this is how they came up with having this complex instruction set architecture for using the very few transistors there as best as possible. But you see in the case of, well, first of all, none of them is around except 86 in some microprocessors and x86 in, of course, the vastly popular mainstream. However, in x86 they later also, with I think the Pentium, they moved to internal RISC structure. Of course, other like our IDT WinChip previous videos and similars did it first to have here RISC internal. So also there was next gen, so there were in the 90s or so many alternative suppliers of x86 using a RISC core, like Next Gen or something, and IDT WinChip, which sometimes even use RISC, x86 RISC inside something, which was anyway, some of them maybe Next Gen or IDT WinChip. Let's see, where's our P54 here, and do we get here yeah, so the major improvements over the 486 in the P5 microarchitecture include superscalar architecture, 2 database pipelines that allow completing 2 instructions per clock cycle in many cases, and can handle most common simple instructions. RISC proponents had argued that the complicated x86 instruction set would probably never be implemented by a tight pipeline microarchitecture, but the way they do this, of course, nowadays is decoding what we just mentioned in the other live stream with Intel and AMD, the Intel Atom update, the first microarchitecture from Intel in decades to execute x86 instructions natively, because since the P5 or so design, there's even micro op, or I think that probably, let's Google that, Intel Pentium micro op. Or was this the first? Was the Pentium Pro the first micro? Anyway, let's see, is this here? So what many of those I thought up from the Pentium, but maybe the Pentium Pro, that all of yours x86 CPUs from the last decades at home, they all decode, because you see what a nightmare, what a complete cluster F, what an effing cluster F this is, decoding this. So that is certainly totally no fun to implement in a superscalar and so on silicon. So what Intel and AMD and others have, actually others have done before, right? So IDT WinChip and others, we could, by the way, Next Gen CPU. So there were other competitors that many have long forgotten, and for example AMD purchased. So they had an internal, so others, so not even Intel and AMD started with this. So there were competitors in the 90s who did exactly this, of bridging this complex nightmare of an instruction set with an internal high-performance RISC core. And next gen was purchased as written here by AMD, and there also was IDT WinChip of what we have here, IDT WinChip, and also here on previously seen on this channel, and they also used internal RISC, using the experience from the RISC processor market, creating a small and efficient processor similar to the 486 pipelined in-order execution microarchitecture, similar to the design, yada yada yada. I was pretty sure they use also RISC internally. Of course, this designed by Centaur later and ending up at VIA. But as you see here, apparently maybe since the Pentium Pro, so many processors you lose overview which exactly started this, but they decode to one can decode any x86, what the decoders are not equal. Okay, so there are 3 instructions. So there you see how complex is x86. In the Pentium Pro, as written here in this article, there were even 3, not 1, not 2, but 3 instruction decoders. Decoder, of course, that part of the microprocessor that is reading after fetching the instruction from memory, decoding it and scheduling it to the instruction pipeline that in modern CPUs there are multiple of. And so 3 instruction decoders that are not equal in capability. Only one can decode any. So yeah, so complex that you have 3 and only one can decode any of this. We have it here somewhere. Yeah. So all of those instructions here on x86, all these many fancy ones, and they are so complex also. Yeah, load local descriptor table and fun stuff like this, right? LLD, load local descriptor table. Here is 0F00 register or memory 16. So complex that you need 3 of those, not all created equal. And the other 2 can only decode simple x86 instructions. This restricts the Pentium Pro ability to decode multiple instructions simultaneously, limiting superscalar execution, meaning you can only issue 2 or 3 instructions if the instructions are simple enough. If they are too complex, then they need to wait for the first and complete decoder to be free. And this x86 instruction decoder here on the Pentium Pro from decades ago decodes this internally to an 180-bit micro operations, micro ops, and there you see the x86 instruction space so complex and convoluted that decoding this variable length garbage here in the Pentium Pro case, all this here variable of whatever there might be, decoding this internally to a fixed 18-bit micro ops. And this is the internal secret sauce that Intel and AMD kept changing, and nobody sees actually. Basically, this modern x86 CPUs RISC internally and hiding this implementation, exact implementation, whatever they're using, the internal micro ops, and feeding this legacy highly compressed yet super complex instruction stream and trying to execute it as fast as possible. Micro ops, so commons micro ops roughly compared correspond to internal pipeline steps, I suppose. Yeah, so of course the Intel and AMD are not disclosing this, makes not much sense. So they are mapping this super complex variable length format to a fixed length format here, in this case 118-bit, to decode here of all the registers, and memory, immediate and so on. And yeah, this is of course secret, only sometimes a little bit leaked, and for some RISC-like operations, because it is extremely hard and challenging to try to superscalar execute this variable length garbage. It's of course nicely and compact memory compressed with all this load and stores inside, but neither fun to write a compiler, certainly well, highly efficient, quite difficult, quite challenging for a machine compiler algorithm to generate and schedule this kind of, for example, just probably had here this as an example. So even in modern code, this instruction of 14 opcode 14 probably in modern programs rarely used, if ever, because this is Edvis Carey. Anyway, it doesn't matter. Edvis Carey, because this is only the AL register, meaning the first 8-bit, the low part of the AX register. So for a compiler, extremely impossible to generate this opcode. So this, yeah, making the best use of this, highly difficult. And again, for this very special instruction, not only is it immediate 8-bit, so this would be you have an 8-bit magic number and you would want to add an 8-bit magic number in your C or Rust program to an AL register, which also you could actually, this makes somewhat sense if you could still have a 0. It could still, okay, so maybe it is sometimes generated because you could have a 0'd register and you would want to load an 8-bit like 0 or 1 like a boolean. So yeah, maybe it's sometimes used, but you see this instructions highly specialized, so not easy to generate. And fun fact, eventually over the coming years, maybe already this winter, I will try to make an extremely tiny code generator for all the popular architectures because we have them here anyway. And so I will try to generate, of course, not all of them. So I will try, because mostly I want to do this for RISC-V, because I'm curious. This is all this stuff you always, if you're in computer science, you always wanted to do some small compiler stuff and to develop and research some just-in-time compiler stuff. I will try to write a extremely tiny, like maybe like 1,000 lines of code, like super tiny code generator for x86 and PowerPC, MIPS, and SPARC and RISC-V. So I think for the RISC architectures that is relatively simple, because most, again, similar to x86, we would not need to use most of the instructions. This code generator would be, of course, tiny and inefficient, and just to get the most basic stuff working, meaning implementing add, sub, end and or and jump and call and so on, and load and store without all the special variants, just like the most minimal set of working Turing machine kind of example. And also because x86 is so complex here in this regard, most likely I will try to make this RISC-like and make there some like internally always use like load, store, and add and or and stuff, and then map this internal representation of most minimal, keep it stupid simple, to somehow generate x86 complex stuff, variable lengths, goodness out of that. So Joe asks the new atom. So this is the new atom core. We made a previous video. You probably want to watch those, but if you take a look here on this video here, this is only the atom core. However, as I called out here in this video here, somewhere like two below this Tremont core, this atom core, maybe it is used also in, hello, can we pause it? Maybe it is also used in a pure atom, but the big change is also, as per this rumors and video, that Intel might combine this atom core to other Core i7 and Core i9, so that you have this ARM kind of big and little setup of big performance cores and little energy efficient doing stuff. And according to this rumor there that we read and made this video about, this atom core, not sure if that is true, but rumors are, or maybe Intel said this, is the first processor since probably then the Pentium, I guess, that is directly executing this variable length complex instruction set again. But yeah, time will show. As much as when we get more details, then we take a closer look. Joe doesn't understand why Google V8 engine only supports CISC difficult architectures and none of the RISC. It is a shame, would be easier to bytecode. I would think it for sure must support ARM, right? They certainly don't support PowerPC and MIPS because there is not really a huge market for that. But V8, JIT, ARM, I'm pretty sure it would support ARM. Here's V8 on ARM, 5 times better. So ARM is also pretty RISC-like for the most part. ARM is actually the one architecture that is a little bit further away from this other classic Unix workstation CPUs, but that's probably something, as this video is already too long for another day. And that V8 only supports ARM and x86 is because that is a 95% target market of Google for x86 PCs and ARM mobile stuff, and SPARC, MIPS, PowerPC certainly not something that Google encounters very often, except maybe on server for Node.js. But this is also, yeah, let's see if I can get some small and stupid JIT running another day in the winter. Don't forget to share, like and subscribe for that. Also Pico RISC-V on the FPGA. I get back to work and do some MIPS SGI origin testing stuff now. Hope you learned something and found this interesting, this quick overview. As you see, when we just give you an overview, then it's already half an hour or something of, where is even my, half an hour, 1 hour. Anyway, hope you learned something, and see you soon for all the next live streams and tinkering and programming here.